In this lecture, I want to introduce stochastic truth table. So here's a truth table. This is a truth table for two atomic propositions, P and Q. I'm not going to list the other formulas in this truth table since they don't matter. Since there are two atomic propositions, there are going to be 4 rows of the truth table. So for example here, row 3 is the truth value assignment that assigns false, or F, to P, and true, or T, to Q. Now, a stochastic truth table is simply a truth table where each row is going to be assigned a number. So P1, P2, P3, and P4, those are all numbers. And it's assumed that 2 things are true. 1, each number is greater than or equal to 0. And 2, the sum of all the numbers assigned to the rows must be equal to 1. That means that P1 plus P2 plus P3 plus P4 must be equal to 1. This also means that we can say that every number Pi is going to be greater than or equal to 0. That's from property 1. And it has to be, of course, less than or equal to 1. That's because the sum of all these numbers has to be 1. So each number by itself can be at most 1. Now, a little bit more formally, we can say that a stochastic truth table is just a truth table where each row I, so I is ranging over the number of the rows, so there's 4 rows, so I ranges from 1 to 4, is assigned a number P sub I, such that for each I, Pi is greater than or equal to 0, and the sum of the Pi's is equal to 1. That's what this notation right here is, this big sigma sub I of P sub I. That's just a shorthand for writing P1 plus P2 plus P3 plus P4. So this is just kind of a short mathematically precise way of saying the sum of the Pi is equal to 1. Pi, the number assigned to the row I, is intended to measure how likely or how probable it is that the situation described by row I obtains. I might say it's the probability of row I. So for example, P2 is the measure of how likely it is that P is true and Q is false. So in some situation, how likely is it that P is true and Q is false? So for example, here's a stochastic truth table. 2/3 is assigned to the first row, 1/6 to the second row, 1/12 to the third row, and 1/12 to the fourth row. The sum of those numbers is equal to 1, and then we can say the probability that P is true and Q is true is equal to 2/3. And for example, the probability that P is false and Q is false is 1/12. Here's another example. Perhaps each row is assigned the same probability. So in that case, each row is assigned 1/4 or 25%. And finally, here's another example. Note that I'm assigning 0 to some of these rows. So that means the probability that P is true and Q is false is 0. So while it's a perhaps logical possibility, it is certain not to obtain. So I'll say more about what it means to assign probabilities 0 to rows later on. There are 4 things you need to remember about stochastic truth tables. First of all, any assignment of non-negative numbers that sum to 1 can be used to form a stochastic truth table. Second, since the sum must be 1, and the numbers assigned to a row in a stochastic truth table are all greater than or equal to 0, no row is assigned a number greater than 1. That means the numbers assigned to each row must be between 0 and 1. Third, if a row is assigned 1, then that row is certain to obtain, and all other rows must be assigned 0. And finally, if a row is assigned 0, then it is a logical possibility that certainly will not happen. So, for example, being dealt a red spade from a normal deck of cards, or flipping a coin and having the coin land on its side. It's a logical possibility that a coin might land on its side, but the probability of that happening is typically taken to be 0.